All right, so welcome to the presentation on the mechanical engineering program. I'm going to talk briefly about, so my name is Nick Kruglikov. I know some of you, I guess, from class, but I'm going to talk briefly on a little bit about the program, from term 3 to term 8. And then we're going to have different speakers talk about different sort of thematic areas of the program. And hopefully we'll have time for questions at the end. Well, we will have time for questions at the end. So that's a little bit about me. I'm currently the mechanical discipline chair. I work in, and I'll talk a little bit at the end because I've asked each of the presenters to also talk about what they do, the kind of what their interests are, and because we're all in sort of different fields of mechanical engineering. So I'll do that. But I work on sensor systems, intelligent sensor systems for autonomous vehicles. And I teach courses in Mechatronics, machine vision, and some of the mechanical design courses. And Engineering 1 quite often. So a little bit about mechanical engineering. So normally, I think it's a fair statement to say it's usually referred to as the broadest and the most versatile program. It covers a number of different areas. And as a result, it's the largest program at MUN, the largest engineering program at MUN. And it's usually the largest program in most universities, even in the US. It tends to be the largest. Entrance into term 3, so when you complete Engineering 1, entrance into term 3 is competitive, but we also have the largest cap. So we technically we cap at 75 students, but usually we go over, so it's about 80 or so. And often the best students do come into mechanical. Like if you look at the top 30 or so, they'll have averages over 80, I'd say. But because the program is quite large, if to get in the past, it's been sort of in the low 70s, to give you an idea, because somebody's going to ask me that question. But it may change, but that's usually where it is to get admitted. All right. So this is what engineers do, or what mechanical engineers do. And you'll learn more about this from the various speakers. But again, it's a broad discipline, so and a lot of our graduates will obviously work in the energy sector, which is probably the #1 employer for mechanical engineering students. And a lot of the co-ops are in the energy sector. But I'm not necessarily only referring to petroleum and gas. A lot of them will work in renewable energy, and you'll learn a little bit more about that. Wind and hydro, wave. Aerospace, I have 2 up there. Aerospace and automotive. So many universities in the US will offer programs in aerospace engineering and automotive engineering, but we don't. But there's a lot of overlap with the mechanical program. So Sam over here is an aerospace engineer, and he'll tell you that it's 80% overlap with mechanical, because a lot of the solids and the fluids is the same. Automotive is similar, same idea. It's mostly mechanical engineering. Mechatronics, which I'll talk about later, so actuators, sensors, robotics, that kind of, and controls. Materials, so metallurgy is traditionally, you think of metallurgy when you think about materials, but it's obviously gone beyond that to polymers, composites. So again, I'm not going to always pick on Sam, but he's an aerospace guy who works in composite materials. Defense industry. So aerospace and defense is actually the largest manufacturing sector in the US. So at the moment, anyway, a lot of jobs in the defense industry if you're a mechanical engineer. So I usually give this really bad joke, so I'll tell you anyway. What's the difference between a civil engineer and a mechanical? So mechanicals design weapons and civils design targets. I didn't say it was very funny. Most engineering jokes aren't very funny, by the way. Manufacturing, so computer-aided manufacturing, production technology. These are the ones that you don't really think of so much, but biomedical engineering, drug delivery systems, biomaterials, biomechanics, prosthetics. We're actually looking at, you'll learn more about the streams in a minute, but we're actually pursuing a biomedical stream for the future with the hospital. We're working a lot already with the orthopedic surgeons, so it'll probably take on a biomechanics flavor. And we've got senior project students currently doing projects with the hospital, mostly in orthopedics. Marine engineering, so if you want to design ships, you go to naval, no question. But if you want to look at the systems that are on the ship, which is called marine engineering, so there you're talking about power and propulsion systems, hydraulics, pressure vessel and piping, that tends to be more mechanical engineering. And we are talking in the future, maybe with the navals, of doing a marine engineering option, but we haven't gotten too far on that one. Pharmaceutical and food processing, automation, they kind of go together. So there's a lot of production systems and automation systems in the pharmaceutical and food processing industry. And here's some you don't think about, but electronics. In the electronics industry, one of the biggest concerns is thermal management and cooling of electronics. And those are areas in mechanical engineering. So you'll take courses in heat transfer, for example, that's really what electronic cooling is about. And construction industry, heating, ventilating, and air conditioning systems and building systems normally are in the mechanical domain. And I just have a few more. Product development in general, engineering management, entrepreneurship. We offer a course in Term 8 in entrepreneurship, some of the business aspect. The other one you might not think of is patent law. So a lot of patent lawyers have undergraduate degrees in engineering, not uncommon. Now a little bit about the program. So we have 4 themes that you'll learn about as you go through the program. So thermal, fluid, and energy, mechanics and materials, mechatronics, and petroleum. So this is going term by term, and it's color coded. So thermal fluids is all the things that are in red, mechatronics in green, and so on. So first few semesters you don't have a lot of choice, you're just following the program. Actually, you don't really have a choice except for complementary studies until you get to term 6. So if you look at the program, these are the remaining terms. In term 6 you get your first technical stream elective. All right? So, and then you've got 1 technical stream elective in term 1, 1 in term 6, 2 in term 7, 3 in term 8. And we've packaged these technical streams along thematic lines. So we have 4 technical streams that we offer, where we basically package your technical electives to gain expertise in a certain specific area. So the first one is petroleum, and so there, the first course you'll take in term 6 is offshore petroleum geology and technology. And then there's courses like reservoir engineering, advanced petroleum production engineering. Probably the most popular course in this option we just introduced with a new faculty member in mechanical engineering, Rocky Taylor, which is in Arctic offshore engineering. That's probably the most popular elective now. It's got about 50 students in it in term 8. Then in term 8 you pick 3 of those, so things like pressure vessel piping, corrosion, and then some downstream processing, natural gas, etc., mechanical systems. So you can basically mix and match this. It's 1 elective in term 6, 2 in 7, 3 and 8. The next thematic area is, I'm just showing a slide just to give you an idea. So anything related to petroleum, I've focused on the mechanical aspects. So there's a lot of mechanical hardware and infrastructure on the sea floor now. So that's what I tried to capture here. The other thing you might not think of is there's a lot of automation and robotics now in the offshore. So I got a slide from Subsea 7 with their autonomous vehicle. Materials, mechanics, and design. So in term 6 you'll take computer-aided design, and then you've got courses like industrial materials, mechanical component design. We're going to introduce welding shortly as well. And then courses in machine design, finite element analysis, and there's some overlap. You see corrosion is here as well, because it does overlap. And again, this is very wide, so it could be everything from designing aircraft engines to, this is really a robotic platform, and this is a microstructure. So you'll hopefully learn more about that as we go forward. And Mechatronics, so courses in robotics, component design, maybe machine vision. In Term 7, we offer modeling and simulation of dynamic systems. And there's a couple of new courses in the works as well as part of our growth. And again, this is widespread, so I always mention the best example of a mechatronic system is probably a modern car. Everything's computer controlled, so I show that. But autonomous vehicles, a couple of examples here, and more traditional robotics. And energy systems, so thermal fluids or energy. So this we sort of separated out from petroleum. This is more to do with turbines and power generation. So of course, like heat transfer, mechanical equipment, computational fluid dynamics. So those are the 4 streams, and you'll learn more about them as we go forward. So now we're going to really focus on the streams.
So happy to talk to you all about my favorite topic, right? Thermal fluids and energy. So I find a lot of the time when people, whenever that term comes up, thermal fluids, people sort of look at me a little bit confused by what it means. And if I ever ask, do you know what thermal fluids means? People, I find the most common response is, hot fluids or hot. So it usually has to do with heat, right? So, which is sort of true, but not 100% true. And the fact that, thermal more refers to energy overall, right? So heat is a form of energy, but there's also many more forms of energy. So with thermal fluids and energy engineering, we're looking at all the different ways that you can use energy in its various forms to try to basically give useful applications for people, which is very important for a number of things, right? So some of the most important, I guess would be the top one here, power production, right? So power production, of course, is immensely important to everything to do with our lives. You have one day without power, right? And it's just chaos because everything we use is all using power. So it's very important for us, but it's also very important for, addressing issues that are important worldwide. You have problems with food shortages or unclean water. Well, with enough energy, these can also be addressed, right? You can make fertilizers, and you can improve the soil. You can remove salt from water. You can pump water long distances. These are all applications that involve, having enough energy. So steam and gas power plants are some of the more common ways that we use to produce large amounts of energy worldwide. In Canada, of course, hydroelectric is also very important. And then a growing area, renewable energy, of course, one of my favorites. So here, I sort of have it divided into 4 main areas, but in the time I have, I can't really cover thermal fluids in every aspect of it, right? It's a very broad field. There's many different things that could be investigated. But transportation, of course, is highly integrated with thermal fluids. So some of the key ones listed there. You got internal combustion engines everywhere around us. Jet engines, of course, are a very fascinating piece of engineering. Fuel cells, some people might, if you have a little bit of knowledge of fuel cells, you might think, well, how is that really a thermal fluid when it's more of an electrical chemical process, right? But there's still lots of issues of thermal management, of bringing the hydrogen or other fuel to the fuel cell, the overall power output. These are all important issues as well. Of course, in this area, in this region, resource extraction for oil and gas has many thermal fluid applications. Even if it's not in the, if it's in this technical stream, you still have things with drilling, with pipelines, with subsea tiebacks, which all have a lot of thermal fluid implications to them. And then, thermal management. So it was mentioned about, electronics, cooling. So you all have, probably, I would assume, had issues in the past. You have an old laptop or something, and it's overheating, right? So the thermal management system isn't really performing its job anymore. So by improving these systems, improving the ability to dissipate the heat, you can improve the performance of your computer, make it last longer, make it work better. On the top picture here, you have some wind turbines, and here in Newfoundland, there's an interesting experimental kind of research installation where they have wind turbines coupled with hydrogen production and a diesel generator for this remote community. So, when they're not using all the power from the wind, they produce some hydrogen, and then when they need the power, use the hydrogen to make power. And this is all just to offset the diesel costs, right? So the diesel cost and the pollution that is associated with it, burning it. And I think this is sort of to me, it's a very beautiful looking picture. And so it's a very simple form of energy storage, which is another important aspect of thermal fluids and energy engineering. And so this one here, you just have these two reservoirs, and by pumping water to the top reservoir when there's excess power, right? So say at night, when there's this excess energy that's not needed, and then when it's needed, say in the peak times of the day, drain it back down, and in between have a reversible pump turbine, and so you can get power out when needed. So a complicated HVAC system, again, another important aspect. So back to power production, right? So here we have many transportation sort of applications of thermal fluids that are needed, as well as some stationary. So here, you have the oil power plant in Newfoundland, which is supplying most of St. John's power. At the top here have a nuclear power plant in Ontario. So nuclear provides around 50% of Ontario's power. And again, it's not just the nuclear engineering that's important, right? So you have your reactor creating vast amounts of heat, and you have to control this heat and then use this heat to create electricity. So all thermal fluids are energy engineering applications. And so we have some military vessels here, right? And so huge amounts of power needed to move those, right? So here would be this is an engine room in a ship. You can see it's a very complicated, large-scale engineering system. You have high-performance automobiles, which you have the engines, of course, but also you have the aerodynamics issues as well that all have to be considered, as well as weight, right, and longevity. And maybe here we have a more kind of laid-back way of transportation, right? Using the energy from the wind. So another thermal fluid application. So this is probably my favorite area of thermal fluids. So I think sort of a widespread issue these days that the pollution caused from energy production between all the cars, between the coal power plants, and all this combustion and all the releases into the atmosphere and into the water, right? So people have a lot of concerns. And so here are some ways of sort of addressing it. So I think this is sort of a very interesting building and quite visually pleasing, right? So it's the Bahrain World Trade Center. And they have these 3 skywalks here with wind turbine on each one, right? So the 2 buildings, they're sort of shaped like a sail, and they're funneling the wind through the wind turbines in between. And so it's creating a lot of power. It's an interesting application, I think, of some sort of modern ways of implementing renewable energy systems to offset traditional methods of power production. Here's the Lower Churchill project, a conceptualization up in Labrador. So hydroelectric, of course, is a huge, opportunity for Canada as a whole, right? So in Quebec, for example, 80 to 90% of their power is produced by hydroelectric, and this makes them a large exporter of power, whereas a lot of the other provinces do not export nearly as much, and it's a very beneficial to their economy, as well as an environmentally friendly and renewable method. And then you have here, this is, I think, a very nice looking picture of a solar thermal power plant. So a lot of people, when they think of solar power, they think of the PV cells, right? The photovoltaics. But they can also use just the heat from the sun as well. So these are all mirrors all around this one central tower. And by directing all the sun to the focal point at the top, you can create very, very hot temperatures and use that for creating either steam or a pressure difference in a gas to create electricity. And then they also have high performance fuel cell vehicles now. And so my last slide, kind of just trying to give an overview of my research. So my favorite area really to research is in renewable energy systems. So among hydrogen production and solar, but wind is probably the area I focus the most. So I hope you can see it okay. Here we see the amount of energy produced per province for wind. And so Canada's doing well. It's one of the higher producers of wind, particularly per capita. But here I got this wind energy density map of Canada. And it's a little hard to make out, but here's the coast of BC, and the east coast of Newfoundland here in red, right? So between 8 and 9 average wind speed, 8 and 9 meters per second. Very, very high potential for wind power in this province to be exploited, right? But the problem with these conditions is that, as you all know, there's sometimes very, very strong winds, which can almost be too strong for the structures. It's also changing direction a lot, which gives a lot of implications. All the rain, all the ice. These are all areas that sort of need to be improved to really optimize the wind energy potential in Newfoundland. So these are the areas that I'm looking at, trying to research, looking at trying to put wind turbines for these remote communities, which are currently using diesel generation, ways that you can store energy from the wind to use it, when it's needed, since the wind is not blowing necessarily when you want the power to be produced. And so I've also done a little bit of research on this airplane, which I thought was an interesting one to show. And it's supposed to be a seaplane, right, where it can land on water. That's why the wing is at the bottom there. And so by removing the pontoons, you improve the aerodynamic efficiency, right? And it's also supposed to handle better on the water as well. So it has some implications there of improving the lift while limiting the drag, which are some more thermal fluid applications. And then sort of pipelines, multi-phase flows. So here's just some pipelines in North America. So you can see it's a pretty intricate network, and these are only for oil and gas. There's more pipelines if you want to look at other commodities. And this pipeline here is not actually for oil and gas. This one is in Hawaii, and what it uses is the temperature difference as you go vertically in the ocean, and using that temperature difference to produce energy. So it's sort of my other area of research, looking at the multi-phase flows of these different systems and trying to optimize the movement and sort of characterize the physiochemical processes involved. So I hope that some of you find this area interesting, and if you do, I encourage you to look at thermal fluids and energy systems.
So next up is Professor Sam Nakla, who's going to give a bit of an overview about solid mechanics.
Solid mechanics is simply when you want to build something, you got to make sure that it's going to take the weight, it's going to take the load, it's going to take the thermal stresses, thermal fluids, it's going to take the vibrations. So you're going to make sure that the design is simply comfortable in terms of dimensions, in terms of everything, and it's going to be safe to use. So let's go ahead and see how it all started. It started with Archimedes in the beginning, and it ended with the Microstructure, but you can see a whole lot of famous names in between. But we're not going to go too much into history now. We invited Tommy Pickles to help us with some application here. So, a simple design, a design of a slide. So let's say that you want to design that slide. First of all, how sliding will take place. You studied that in 1010, or you're about to. Simply, will he bounce down or tumble down, or from equilibrium equations, he's going to simply slide like that. So you know how the load is going to be acting on the slide, which is the structure. So this is the first unknown in a set of unknowns. And now when you go for the slide design, you know that you have the applied load, whether Tommy is a tiny guy or a much bigger guy. And the manner in which he slides, the objective of the design is that the slide is not going to deform too much under Tommy's weight, because that's going to be dangerous for Tommy, and it's not going to break while Tommy is sliding. So this is just a simple application. But we don't design slides in mechanical engineering. We do much more sophisticated stuff. So we design an aircraft from thermal fluids. We get the air loads, the heating that takes place in the boundary layer, and we design the stresses based on the stresses. Other applications is engines, like internal combustion engine all the way to the left, or parts of an engine, like a turbine blade or what have you. All these things are mainly about materials and loading in terms of temperature or air loads or what have you. We come up with a design for in terms of solid mechanics. Or we do crash worseness for cars. So instead of putting somebody in a car and experiment with hitting it with a wall, we do a simulation, and through that simulation, we will be able to get an idea about the crash worseness of a new car. Here are some applications of what I do. Normally, I do composite materials, but solid mechanics is a widespread field, so it goes everywhere. Composite materials, we start by these tiny panels here. These tiny panels has some aspect to it which is very peculiar. They have two shapes. You know, like you have to see it. If you're coming to the open house, you're going to see it. So how to use piezoelectric actuators to make them pop from one shape to another. And then how to build a morphing wing for a tiny aircraft, uninhabited aerial vehicle. So this was one application. Another application which goes into prosthetics. So the prosthetic socket for the lower limb is made out of carbon fibers. So it's made out of fiber braiding. And normally it would break at the stem here. So the testing and the design of it. How to make it lighter and still stronger. So, as well, design of stuff that's related to an aircraft. So this is a radome design. You know what is a radome? Normally you have communication, like equipment on an aircraft, and you want to put it inside or underbelly of the aircraft, but at the same time you want to cover it with something that's not going to shield the radio waves. So you build something like that with composites. So this is a fiberglass sandwich core. It's a Roacell fiber core. Or one more application, which was a parametric design of the fan stage. Just the fan stage of an engine. So simply, if you know that the engine requirements, you plug in the numbers, and in CATIA, it would show exactly right away, pop up. The CATIA is a CAD system, by the way, computer-aided design. It's going to pop up the design, a visualization of the design that you may want to adopt. Today, I took the liberty to do a search using Indeed Canada, just typing stress engineer, and I believe that there is a number here like 319. So stress engineer, airframe, Bombardier, all these. So some of them are posted like 12 days ago, some are 14 hours ago. So there is a huge market for that. There is a huge market and demand for stress engineers. And then I conclude, mechanical engineering, the profession of intelligent people. Welcome to Memorial. Thank you.
So I don't know how many of you know Jeff Rideout. You might have had him in engineering, maybe not. He hasn't taught engineering one in a while, but so he'll be talking about system dynamics, mechanics.
All right, thanks, Nick. So I'm going to be first talking about really the first dynamics course you'll do in the fall, which is an extension of statics, except now the sum of the forces is not 0, it's MA. But that turns out to be a lot more challenging than people realize. This is the course where people say, I get all the other courses, but dynamics is blowing my mind. So, well, while your mind's being blown, you'll be aware that you're learning some very useful and interesting things about how the world works. Here are a couple of typical dynamics problems which I plucked out of the book because they're in my area of interest, which is vehicle dynamics. If you've got a ladder propped up in the back of this pickup truck, how fast can you accelerate before that ladder starts to tip back over the tailgate and crashes down onto the lane behind you? In this problem, we ask, how fast can the truck accelerate with this crate on the back? So let me put the question to you first of all. What are some things that might happen if you accelerate too fast? The crate could fall off, right? So it could slip off. So here's an example where in statics, your equilibrium condition could not be maintained. There's not enough static friction to maintain equilibrium. What else could happen? That could be bad. The crate, if the crate doesn't slip, what else might it do? If this was a refrigerator, what might it do instead of slipping? It might tip over. Okay, so there's dire consequence B. If you accelerate too fast, maybe the rear tires break loose. You can accelerate the fastest if you keep your tires rolling without slip. You keep them in the static friction zone. Because we know static friction forces are higher than kinetic friction forces. The truck may do a wheelie. Unlikely, but it's one of those things that could happen. So to analyze this, you need to apply Newton's laws. So some of the forces is MA. Some of the moments about the center of gravity of the truck and the crate equals inertia times angular acceleration. So that's the new wrinkle that dynamics brings. So dynamics is first of all a study of motion, how to mathematically describe motion, and then how to figure out what forces are causing that motion. Do you think it makes sense, this is a trick question, but someone take the bait anyway. Do you think it makes sense to model a vehicle as a particle with negligible size and no rotation, or to model the truck as a rigid body where the size and the shape matters? What does your gut tell you? Anybody? Anybody? Rigid body. That makes sense. It sort of depends. And now I'm going to get into system modeling. When you're trying to predict something with computer simulation, you need a model of the system. And sometimes a really simple model is useful. It gives you a rough answer very quickly. A complicated model gives you a better answer, but it may take days. If you want to know how fast this car can go up over the hill before the tires lift off the ground, it doesn't really matter how long the car is, what the wheelbase is. You're concerned with the normal acceleration. How much speed can you carry into this curve and still keep your tires on the ground? Now, if this is Tommy Pickles going down the slide, okay, let's say it's you in the car. When you hit the valley, what do you feel? The car goes down in the dip and comes up at really high speed. You feel your heart going down, right? And here you feel your stomach coming up in your throat. That's all because you're being accelerated. The loads on you are different. Now the loads on the road are also different. When Tommy Pickles goes down the slide, his acceleration is going to change the forces on the slide. So it's actually deceptively difficult to figure out where the peak loads on that slide are going to occur. If you have a moderate load in the middle, you'll get a certain deflection. If you have a higher load at the bottom, you may get less deflection and you may get more. So dynamics and solid mechanics are intertwined. If you want to predict how fast you can go into a decreasing radius turn, again, modeling the car as a particle is fine. But when you dig a little deeper, the amount of cornering forces that the tires can generate to keep you on that curve depends on, well, the steering angle for one thing. So to get more precise results, now we start thinking of the car as a rigid body. If we want to predict not just that the car spins out, but exactly how fast the yaw angle builds up. Now we need a more complicated rigid body model. So we get into that in the second half of dynamics. We also move then into mechanisms in term 4, where we predict how is the angle of these tires going to change as the suspension deflects. And you can design suspension mechanisms that allow the vehicle to lean into the turn. You also learn interesting things about how the world works. For example, Coriolis Effects. This is a dynamic acceleration related principle which explains why if high pressure air goes into a low pressure zone in the northern hemisphere, air coming up from the south goes this way, air coming down from the north goes that way, and you get this cyclonic hurricane effect. An iceberg that is pushed due south from the North Pole is actually going to drift westward because of the rotation of the Earth. So we learned how to talk about that mathematically. If there's any baseball fans here, maybe your dad or mom will tell you about Jim Rice. He was one of the strongest, we believe, non-steroid enhanced baseball players ever. And 3 times in his career, he broke his bat, not by hitting the ball, but just by stopping his swing. So he stopped his swing so quickly that the bat actually snapped off. The bat has some mass out here, and if he's got that bat going at full speed and he stops it, that mass wants to keep going. In something deformable like this, you can see the bending stresses that build up. We talk about those sorts of inertial forces. We can predict how much of a notch would have to be in that bat in order for it to snap if you tried to check his swing. So that ties into solid mechanics. We can calculate where the sweet spot of the bat is, where when he hits it, he doesn't feel his hands being jerked one way or the other. If you know how far a golf ball travels, and if you know its initial angle coming off the club, and if you know how long the club head contacted the ball, then you can estimate the impulsive force on the club. So that's useful. And you just saw some deformable mechanics going on there with that golf ball. Again, all dynamics and mechanics. If you see a picture of a big container yard, they have these level luffing cranes. If you size these links and locate their endpoints properly, you can extend the crane and you can move a load horizontally. So you can move a container horizontally in over the deck of the ship. If you just consider the weight of the load, here's the force required in the hydraulic cylinders that move that crane. If you consider the inertial dynamic forces associated with speeding up these links and slowing them down, dynamic forces are often in design either omitted or underestimated, but they usually are critical. So dynamics is essential if you want to do design. In my Term 8 engine dynamics course, we talk about engine shaking forces, which engine types are smoother than others, where to put balance shafts to smooth out vibration, how to determine how big they are, and exactly where to put them. So in my research, I do a bit of vehicle dynamics research. I also do vibration of oil well drill strings. Even though these drill strings are made of rugged-looking steel pipe, they actually bend and vibrate in a number of different ways. So there's a course on vibrations where you can learn about axial, torsional, or bending vibrations. All of these occur simultaneously in oil well drilling, which makes it an interesting research area. So we have ways of simplifying the dynamics of the big, long, continuous pipe. We can actually use a lot of Term 3 theory and Term 6 theory to predict the onset of vibration in an oil well. So there's an unbalance down here near the bit. And if we spin the drill string up, and these drill strings are several kilometers long, we'll see some vibration building up here in the center of one of the long spans. So we get a lot of bending vibration. And then after a while, the drill string starts to snake its way around the hole. It starts to whirl. So predicting this sort of vibration is essential for predicting when the tools that allow you to steer the drill string. You need to not subject those tools to excessive forces. So you need to understand how the drill string vibrates. with these models, we can predict when stick slip occurs in the drill string, when the bit actually slams up and down off the bottom of the hole. And my other research area is in trying to predict the strength of wooden hydro poles. We take poles in the field, we hit them with a sledgehammer, we measure their response. And from the vibration response, we can figure out the natural frequencies at which it wants to vibrate. And we can figure out how much damping there is in the system, how quickly those vibrations go away. You think of a diving board as vibrating at this kind of low frequency, but there's lots of other complicated vibrations going on in there as well. Here there's low frequency vibration like this, and there's high frequency vibration on top of it. By measuring all those different vibration modes of a pole, we can actually predict its strength. Okay, so here we need dynamics, vibrations, solid mechanics, we need modeling, finite element, simpler models. So there's dynamics, mechanics, and vibrations. Lots to talk about. So hopefully we'll see you guys in the fall.
So our next speaker is Amy Shao, who's going to give a brief talk on material.
My name is Dr. Shao, Amy Shao, and I'm the materials professor in mechanical engineering. I want to give you a quick, very brief synopsis on what materials is and what you would learn as a mechanical engineer. So my first taster, if you will, is you have a look at this. We're all familiar with Coke bottles. And you can see that there's differences between the 3 different types of Coke bottles. What are some obvious differences? Besides materials, yeah, what do you see? What kind of materials are there? More specifically, I mean, you see plastic, see glass, see a tin can, right? And then you see the different shapes, right? And you also see that perhaps there are different shapes and different materials for different reasons, for performance, whether it's a single serving for lots of people, for keeping thermal, for keeping it cold better, longer, etc. And maybe even how this piece of this device, if you will, this beverage container will be recycled or not able to be recycled. So if you go on to the next slide, you see here metals, glass, polyethylene, polymer PET plastic. And if you go on to the next slide, you see that material science is all about these 4 things: processing, structure, properties, and performance. And I purposely put performance on the bottom because normally as engineers we put it at the very top. That's our end goal, to make sure the materials perform as they want to. But in order for the materials to perform as we want to, we have to look at the microstructure, how we make it, the processing, and also the properties. The structure and also the mechanical properties, the thermal properties, magnetic properties, materials properties. So really, I like to put it as a steering wheel so that whatever we're interested in as an engineer, we just turn it around. If we're most interested in processing, when we look at that. If we're most interested in analyzing the mechanical properties, when we look at that. Of course, keeping in mind that the end result is that the material performs very well. Next slide. So this is a very sort of busy slide here, but it just shows that we've been using materials since the dawn of humankind, right, of mankind. And you can look at wood and skins and stone and earth sciences. They would be interested in looking at materials of that sort. But as engineers and mechanical engineers, we're interested in metals, modern day materials, how they're formed, how they're made, and how we get the properties that we want from modern materials: metals, polymers, composites, ceramics, glasses, etc. So if you look at the next slide, you see all sorts of everyday materials. If you look in your backpack, what do you have in there? You've probably got a whole bunch of plastic for your iPhone case, for your notebook, for your pencil, for your pen, and this is the kind of stuff that, the kind of materials and the kind of processing that we would look at as mechanical engineers, because we are interested in the design, the fabrication, the improvement of the selection of materials for all of these different applications there. So you see, go back to the previous slide, you see metals for the silverware, for coins, you see the helmet, the bottles, the wheels, pool table balls, brick, porcelain, all of those things that we use, we study as a materials people. So next slide, how is materials applied in engineering applications? Last year I asked this question and hardly anyone knew who this guy on the top left was, but who is this guy on the top left? Yes, of course. Now we know who he is because he's gone through space, come back down. But if you look at his spacesuit, that is a unique material that's designed for the temperature gradients in space, hot, cold, keeping him well insulated, well hydrated, or not sweaty. If you look at his helmet, if you look at all the different aspects that, just in that photo, there's quite a number of applications of material science, processing, performance, properties, and microstructure. And if you look down here, this is one of the ships that usually come into the harbor, and there's me standing in front of it. And you see, even with the hull, with the shape and the type of metal that's being used, where we're looking at materials as well. So materials has a lot of different applications, and it really does fit in with mechanical engineering, which is probably the most flexible or versatile type of engineering you could find in our program here. And you, as a mechanical engineer, you actually get the most comprehensive coverage of material science. There are several courses that talk about materials. So next slide. Another example is something that I do here is biomechanical testing. And what's inherent here is materials application. So if you look at that, those are not real bones, but they're sawbones. So they have the same properties or density as if it's your wrist bone. And I'm pointing to this because that's a wrist bone here. And what we're looking at is a wrist bone fractures. You see there's little cuts at the tip of the top of each bone there. And you'll see that there's different plates. So what we're looking at here is not only the design of the plates, the choice of material for the plates, and also how well they're going to withstand cyclic loading. So we're looking at mechanical properties, materials, and design. I'm not going to show the video for the sake of time, but if you're ever interested, come and find me and we can actually, I can show you that test in lab, or I can show you some of the videos. It's maybe less exciting. Another thing, another application of materials is, I talked about microstructure. So materials science people, materials engineers, mechanical, you will learn this, if you choose mechanical, is using microscopy to analyze what structure actually looks on the tiny, tiny micro scale. So what you see here on the left is an example of, well, in both pictures, example of brittle and ductile fracture, and understanding what that means. What causes brittle fracture, what causes ductile fracture, high impact, low impact, strain rate, all of those things that kind of ties into even what Dr. Rideout was saying when he was talking about the bat. He was talking about in terms of forces, but all I could think of is what kind of material was that bat? And what were the properties of that bat? Or the golf ball? What was the material of the golf ball that made it withstand those kinds of forces and stresses? So that's another example of material science. And then the last one, I think, last but not least, is a lot of the work I do here, because of where we are, is in corrosion. So materials corrosion testing, microstructural characterization is big. And there's quite a number of projects that I work on related to corrosion. And on the right, you see some other microstructure pictures of steel after it's been exposed to chlorine. So highly acidic, high pH or low pH, highly acidic environments. And you see there, what you see is there's a bunch of blistering, or one type of corrosion that's occurring on the bottom image versus the top, less exposure to parts per million of chlorine. So next slide, to try to sum everything up. I shouldn't put that photo there because you can see me right here, but all the things that I do here and the things that you will study here as a mechanical engineer, well, all the things that I do here, offshore oil and gas, the biomechanical testing, orthopedic rehabilitation in particular, corrosion, mechanical characterization, microstructural characterization. And then I have there as a side note, I also wear a different hat besides the materials engineering, is I look after the Master of Engineering Management program. So we do have this interest from engineering students who may want to pursue their MBA or pursue leadership or management, and that's also what I look after there. So I have that little bullet there as well. If you have any questions, please feel free to stop by my office or send me an email. I can talk to you about material science and how it applies to mechanical engineering. Thanks.
All right. Now I've only got a couple of minutes because I went last. I took one for the team. So I'm going to talk briefly about mechatronics. And I'm going to start with the definition, because I might have talked about this in 1040 a little bit, but mechatronics is kind of one of the newer fields for mechanical engineering. And a lot of people look at it as sort of it's electromechanical systems, but it's really more than that. This is the ASME definition, which is the American Society of Mechanical Engineers. They define it as a blending of mechanics and electronics in the design and control of products such as cameras, automobiles, airbags, industrial robots. But this is the definition that I prefer. It's really a design philosophy that encourages the engineer to keep sort of the big picture in mind when you're designing something and making intelligent trade-offs between the mechanical design and the control or the computer programming part. So it's a little bit more than just blending electronics and mechanics. It's really how you think about design when you're designing modern sort of products and systems. And the advantages to mechatronics, it's shorter design cycles in many cases. You can get to a product faster, lower costs, and sometimes elegant solutions to design problems that you can't normally find if you stay within your narrow area of electrical or mechanical or computer engineering. So I've got a few examples. So one is aerial robotics. It's clearly a mechatronic sort of device or system because you've got to worry about the solid mechanics aspects, the control aspects, the aerodynamics, the fluid mechanics. So this is actually a relatively good example. Let's see, and I'll show you maybe. Just quickly, I'll show you a couple of videos that show these quadrotors. And this was at a conference I just went to. These guys in Zurich do all kinds of wacky things with them, but this is balancing an inverted pendulum on a quadrotor. And I won't let it go too long, but just until it gets to the next part. And then they have it goes in a circle and balances it and all this kind of stuff. So there's all kinds of vision systems involved to track where it is. They're controlling the quadrotor. A lot of prediction as to which way the mass is going. A lot of dynamics, actually, similar to what Jeff was talking about. All right. If this works, hopefully. This is something you get to do in term. I showed you the balancing the pendulum. This is in the second mechatronics course in term 7. This is one of the exercises that students do. So it's not on a quadrotor, but it's the same idea. You'll sort of get the idea here. So these students had a bit of an artistic streak to them. So fundamentally, it's the same problem that you saw. But if you look at what's involved, there's the mechanics, there's a ball screw driving the table back and forth. There's sensors that keep track of where the pendulum is, and there's a processor that's controlling it in order to balance. Anyway, that's something that you might do. Another mechatronics example is in high-speed robotics. These are Delta robots. This is at a conference I went to recently in Japan. So for high-speed automation and material handling. This one I've shown in class a few times. This is Big Dog, if you've seen it, a company called Boston Dynamics. It's now bought by Google, actually. Google owns this company. And when I first showed this video to Tom Pike, who some of you know in the lab, he was sure it was two guys in a suit. But it's not. It's actually electrohydraulic. It's all a lot of sensor systems. It uses hydraulics to power it. And this is a little bit about what I do. I'm going to end with this one. So I work on intelligent sensor systems for autonomous vehicles, and this will just give you a brief overview. One of the things we develop is a very precise, high-speed pointing device for tracking objects. And this falls in the area of optomechatronics, it's called. Here you'll see the device. And it's a kind of a parallel robot, but it's, so that's really how it moves. And there's a camera on top that'll track, moving targets in real time. So this was, we were setting up for a conference where we were demoing some of it. All right? And I think I'm going to stop there because maybe I'll get everyone, to take any questions you might have, and feel free to ask anybody almost anything. No, actually none of that ever appears on the transcript. Even when we had the offshore oil and gas option, it never appears in the transcript. And I don't think it's really actually overly important, because if the way our streams are set up, you can actually pick courses between them. We don't really mind. Ultimately, when you go to try to land a job, they're not going to look at the fine print of your transcript. You've got to make the case for what you know, where you worked, what you did, which courses you take. So I think that's really the value. But none of the streams, there's no more real options, and none of the streams actually appear in the transcript for any of the disciplines. You see, if you're interested in robotics, or mechatronics in general, there's no mech part in electrical. The program will focus on electronics and computer applications, but you won't get the mechanical and the dynamics part. So robotics is always a blend. I mean, you can't really do robotics without the dynamics and the mechanisms. So in term 6, you're basically picking your technical stream.